This is ME22's final project video. To start this project, we are given a project proposal description from SKF, which is as follows. The ceramic roller manufacturing line has recently installed 2 new machines to rough and finish and grind the ceramic rollers. While the new machines perform the grinding process well, they are manually loaded and unloaded by an operator. The scope of this project will be to map the current process and automate it to improve efficiency. So with that, we defined our problem statement, which we referenced throughout the whole year of working on the project, and was as follows. Develop an end grind automation process to reduce operator reliance and boost efficiency. After fully defining our problem, we started our work, which consisted of an extensive list of specifications, concept generation, design, detailed technical analysis, simulations, and testing in the pre-shack automation lab, all of which led us to our final design, which is as shown.
As pictured, our final design has a overhead gantry system utilizing a universal robot, which is a UR8 long robot. This robot spans on a track system from end grinder to end grinder. Using the pre-shack automation lab, we were able to simulate our UR8 long robot with similar cobots, which were the UR10 and the UR5. We ended up using the UR10 robot to simulate for proof of concept. As you can see here is the layout for our automation testing in the pre-shack automation lab. As seen in locations 1, 2, 3, and 4 are where 22 millimeter elements are presented to the cobot. As seen in location 5 is where 6 millimeter elements will be presented to the cobot. Location 6 is where a carrier is to be loaded by the robot, and it is secured by pins at location 7 to align the carrier. Once the carrier has been fully loaded with elements, the robot can then slide the carrier away from the pegs over to location 8. Moving to position 8 resembles loading the carrier into the grinder, and moving to position 9 resembles unloading the carrier from the grinder. The carrier is then lifted independently from the elements, freeing them to be unloaded. The robot then places the carrier back to location 6 where another set of elements can be loaded. Lastly, location 10 is where a single element is placed to resemble running it through a tolerance check, and after it is placed there, it is immediately returned back to the carrier. Through testing and evaluation, we quickly discovered that end-of-arm tooling for our problem is not easily accessible, which led us to develop our own 3D printed end-of-arm tooling. This allowed us to efficiently develop many iterations and changes of the tooling. Pictured here is the final design for end-of-arm tooling to grab 22 millimeter diameter end roller elements. Developing tooling that grabbed 3 roller elements at once boosted our efficiency of our process. This video here shows our final developed test run for loading and unloading of 22 millimeter roller bearing elements. Seen here is the single element tolerance check as it is placed in spot 10 and returned back to the carrier. Next, pictured here is our final design for end-of-arm tooling for roller bearing elements that are 6 millimeter in diameter. The following video shows our final developed test run for loading and unloading of 6 millimeter roller bearing elements. we'd like to give a final thank you to Bruce Sweeney and Andy Gortz and everybody at SKF for sponsoring our project.